Alright, let's find our S of n setups here. So here R is 2. Here R is 2. So d1 times 1 minus 2 to the n for 1 minus 2. While over here R is 1/2, which would give us our S of n, our sum formula, 4 times 1 minus 1/2 to the n over 1 minus 1/2. Alright, now, we want to take a moment, we want to graph these on our calculator, and understand this. Y is the sum, x is the n. So the idea is, the larger n gets, the more terms we have, what is happening to the sum? That's the key idea with your graph. Alright, so take a moment, graph those. Hit pause on the video. Alright, so if we're looking at our two graphs, when R is 2, our graph looks like this. So what happens to the sum? As n gets larger and larger and larger, the sum gets larger and larger. So if we were to talk about a sum of an infinite amount of terms, in this situation, it would be infinity. If we're looking at our other graph, when R is 1/2, our graph looks like this. So as n gets larger and larger and larger, what's happening to the sum? The sum kind of plateaus. The sum kind of plateaus, and as we get larger and larger, we approach 8 in this situation. Why is that? Well, in this situation, when we're approaching a horizontal asymptote, with the equation as an R of 1/2, it's said that this represents a convergent series. So a convergent series is a series that sum converges, approaches a number. The sum stays extremely close to the number as n gets larger and larger and larger and larger. Now, I wrote above S of infinity. We don't write that. Right, so we can just write S. If there's just an S, a standalone S, that is a sum of an infinite amount of terms. Now, for the convergent series that we just talked about, the sum at infinity, what are we approaching, is 8. Now, for the other scenario, where R is 2, does this converge on anything? No. Right? So, as n gets larger, the sum gets larger. So it does not approach, it does not go towards any specific number. Now, trying to figure out what about this makes them converge. The key idea is R. And for it to converge, R has to be between -1 and 1. Right? Some people like to write the absolute value of R is less than 1. Now we got this S, which is our sum of infinite terms. But do we have a formula? Do we have a formula that's going to figure out the sum of our infinite amount of terms? So I'm going with our original formula. I'm going to focus on R. If R is 1/2, if we got 1/2 squared, it's 1/4. 1/2 to the third, it's 1/8. 1/2 to the fourth, 1/16. If we raise 1/2 to the 100th power, we get a number, what did my calculator say? 0.5 to the 100th power. We get 7.8 times 10 to the -31. In the end, what is that? It's basically 0. So the larger n gets, 1/2 raised to extremely large numbers gives us 0. So if we raised 1/2 to the infinite power, it's nothing. Right? It's absolutely nothing because there's, as you see here, the larger n gets, 1/2 gets smaller and smaller and smaller and smaller and smaller until it's practically 0. So if we simplify this, our S formula is just T1 over 1 minus R. Now if we go back to that one we just looked at, if we have 1/4 over 1, not 1/4, oops. If we have 4 over 1 minus 1/2, 4 over 1/2, what does that equal? 8. And that's the key thing we saw in the previous problem. Right. Could an arithmetic series converge? Right. No way. Because you are always adding terms. 2, 4, 6, 8, 10, 12. The next term is always progressively getting bigger and bigger and bigger. Or if it's a negative, small, more negative, more negative, more negative. The next term is never getting smaller in the sense of how we go 1/2, 1/4, 1/8, right? 2, 4, 6, 8. Right? It's going up by 2. It's going down by -3. It's going down by 0.5. It's going up by 0.6. It's always changing, getting larger, getting smaller. It's never getting progressively smaller in an exponential setup like that previous problem. Now, what is the main idea today? If R is between 1 and -1, there is a sum infinity. Why? Because it converges. And the idea is that with R being between those two numbers, any 0.5, 0.25 raised to a super large power leaves you with basically nothing there, which leads to the setup where our consecutive terms are getting smaller and smaller and smaller and smaller until we're basically adding 0 to this setup. Right. Do these converge? If so, where do we go to? Alright, so for this problem, R is -1/4, which is great. 42 over 1 minus -1/4, 33.6. This does converge, and that's because the R is between -1 and 1. All right, what do we got here? Well, we have a common difference. The fact is, since this is arithmetic, no, not converging, only geometric. Last one, 5 over 4. Does it converge? No. Why? It's not between -1 and 1. So key thing, we have to have R between -1 and 1. If we have arithmetic, this does not work. If R is greater than 1 or R is less than -1, this does not work either. Alright, here's an issue that I've seen in my class. Well, instead of 6 2/3, I'm going to go 20/3. 20/3 equals 60 times R to the 3 minus 1. 1 over 9 equals R squared. R equals positive -1/3. You get two different R values. A lot of people in my class keep just going with the positive. You get both. And know what? Both of them are between -1 and 1. So when R is 1/3 and R is -1/3, we can find the sums of an infinite series. 60 over 1 minus 1/3. 60 over 1 minus -1/3, which is plus. Our sum here is 90. And our sum here would be 45. And those are the horizontal asymptotes that these graphs are approaching due to converging, due to having R values between -1 and 1. All right, we gotta pretend for this one. T1, T5. All right, real values of R. 1/3 equals 27 times R to the 5 minus 1. 1 over 81 equals R to the 4th. Now, just to show it for everybody's purposes here, I'm going to find all the R values. I could factor equals 0. R equals positive -1/3. R equals positive negative I over 3. We only want those. All right. And they converge because they're between -1 and 1. But we need T1. Our formula has to have T1. So let's go back to what we originally had. 27 equals T1 1/3 to 2 minus 1. T1 is 81. 27 equals T1 times -1/3, 2 minus 1. T1 equals -81. So in this situation, we get two different T1s with two different R's, which overall leads to two different S. 81 over 1 minus 1/3, 121.5. The sum when the R is negative, negative 81 over 1 plus 1/3, negative 60.75. There we have it. Convergent series, people. Key thing, only converges when R is between -1 and 1. And that is because the next term is getting progressively smaller and smaller and smaller and smaller and smaller.